Okay, this is April 19, 2022, and we are continuing this chapter on the magnetic fields. Okay, so what you have to know about, so what we have talked about so far on this chapter. Okay, there is something called the magnetic field. Okay, the Earth has a magnetic field, and some special stones out there also has this magnetic field. This type of magnetic field due to stones was discovered a long time ago in antiquity by the Greeks. Not only we have a magnetic field, we also have what we call a magnetic force. Here you go. Magnetic, this is just a summary, okay? Let's put it here, summary, just to refresh your memory. Magnetic forces act on an electric charge, on a moving, on a moving electric charge. If the charge is moving, you have a force applied, a magnetic force applied to the charge. It all depends how the charge is moving. And then there is, don't forget there is a special relationship for the magnetic force. Here you go. And the relationship is like that. Okay, that's the relationship. Note see that the magnetic force is simultaneously perpendicular to V and B, right? Every time that we have a force, every time that you have a force perpendicular to the velocity vector, okay, what does it mean? Every time, this force will not change, this force does not change the speed of the particle, okay? It may change the direction, but not, it may change the direction of the velocity vector, but not its magnitude. That's what this relationship tells us, okay? So, so what does it mean? We say when something like that happens, we say that the force does not do any work. Okay? Doesn't do any work. The force doesn't change the speed of the particle. Consequently, the force doesn't do any work on the particle. The work done by the magnetic force on an electric charge is zero. In other words, the work done by the magnetic field on an electric charge is zero. And then we can prove that mathematically. There's a very simple mathematical proof for that, and this proof is right in here. Remember that the work done by a given force is F dot delta R, right? So we can do that. Here you go. Let us prove that mathematically. Let us prove that mathematically. That's what doing no work is all about. Okay, if the speed doesn't change, if the particle doesn't increase its speed, then there is no work done by that specific force. Okay, so here you go. the work done by the magnetic force. You go, like that. It's going to be what? It's going to be, you know, F magnetic force dot, let's see if I can get it, dot, yep. Why did they put upstairs there? Huh, interesting. I don't like that. You can do better than that. Here you go. That's the one I like. Okay. Magnetic force, delta R. Uh-oh. Yep, delta R. And equal, oh, equal. Magnetic force is something like that, right? I'm gonna put that between parentheses. You can look it either at, like I said, you can look either in a quantitative fashion or you can look at the mathematical way. A qualitative fashion or the mathematical way, okay? The qualitative fashion is just by explaining that the magnetic force is perpendicular to the velocity vector, okay, and consequently must do no work whatsoever. That's the qualitative explanation. But if you want to do a quantitative explanation, a mathematical explanation, you do what I'm doing right now. Okay? Don't forget you know, this is displacement vector, right? But the v can also be written down in terms of the displacement vector. Here you go. Can be written in terms of this relation here. V can be written down in terms of delta r over delta t. Like that. Okay. And now you look at this relation. Here you go. We have, I'm gonna put, we have, when you cross delta r with b, we are going to get a vector that is perpendicular to delta r. Okay? And when you get a vector perpendicular to delta r, the dot product between this vector perpendicular to delta r is going to be 0 as well. Okay. So that must be 0. So the work done by the magnetic force is 0. So if the particle is moving faster and faster, it's not because of the magnetic force. It's because of some other type of force. The particle may change direction, but it's not going to increase its speed. That's what we have. So that's what you mean by doesn't do any work. Okay, here we go. Here's the proof. Okay. And now we are going to look at the radius of a circular path of an electric charge. Okay, so here you go. Let's, we already said, we already noted that the magnetic force makes an electric charge move, make an electric charge to move in a circular path. Okay, so the question is, what is the radius of this circular path? Circular path. Okay, given B, V, Q, and M, right? What's the radius of the circular path of the charge? So treat that as those is a problem. Okay, so here you go. Let's take a look here. Oh yeah, here you go. It's a little bit off, but that's okay. This is supposed to be a circle, okay? I know why it's like that. Here's the electric charge. This is a positive charge. Like I said, this thing is supposed to be a circle, but because of some let's see if I can. Let me see if I can get this guy right here for you all. Group. I'm going to stretch on the horizontal, and then I'm going to start to look like a circle, right? Better now? Okay. So I was using a different ratio when I drew this made this drawing. So here you go. Here we have a electric charge that's moving perpendicular to the magnetic field. Here, magnetic field lines here. Is a uniform magnetic field. Uniform magnetic field. So I'm asking, the force is going to be perpendicular. Because the force is perpendicular, it's going to bend the velocity of the charge in different directions, and the particle is going to change direction of motion, but not its speed. In the process, the particle is going to describe a circular path of radius r. What is this radius r? Okay, so the force acting in the particle is going to be the magnetic force. There's no other force there. Okay, so assuming, let's put that here, right? Assuming we already know that magnetic force makes an electric charge move in a circular path, along a circular path. Given B, V, Q, and M, Q, M, and the fact that V is perpendicular to B, comma, what is the radius of the circular orbit, circular path, of the circular path? Okay, so here we go. Solution. We're gonna use this result for another device that is important out there, that has important applications. Okay. Going back here again to your drawing. Always make a drawing. Don't try to solve those problems just by math, writing down equations. You have to visualize the problem as well. Okay, so this force here, this magnetic force, you know, and the only is going to be given, let's see here, writing here, magnetic force is going to be given by that equation. Okay, and I'm going to rewrite this. V is perpendicular to B. Consequently, we can write down VQVB times a vector. Uh, okay, that I'm gonna call R hat, the particle, and even better, it's gonna be a negative R hat, because the force is towards the center, is a centripetal force, not a centrifugal force. So it has to be a negative R hat. Going back to the drawing, the magnetic force is going to be the only force acting in this particle. So we can go ahead and state, remember, here you go, because it's the only force acting in the particle, the magnetic force is going to be equal to the net force. Okay, and what else? This magnetic force is going to be M A. there's going to be a centripetal acceleration. Okay, and this centripetal acceleration is going to have a radial direction as well, in the minus r direction. The centripetal acceleration is going to be a positive scalar pointing towards the center of the path of the particle. And we have this relationship using, don't forget, this is Newton's second law. Okay, we have this relationship that we get from Newton's second law. Okay, that's the relationship we get. Okay, we can cancel out r hat and r hat. But we can do something else with the acceleration. From the equation for the centripetal acceleration, let's not forget, I'm going to put here centripetal acceleration. So we specifically identify that as a centripetal acceleration. From the equation of the centripetal acceleration, we know what? We know the centripetal acceleration is v squared over r, right? I'm going to put the mass outside here, outside this ratio, so you can visualize the centripetal acceleration better. And look what we have here. We have now this equation. Okay. V is going to cancel out with the other V. What we want to know, we want to find out this R right in here. I'm going to boldface it so you know what we're looking for. R QVB QVB. V cancel out with the V. MVQB, and that is going to be your the radius of the circular trajectory of your particle. I'm going to put the M there upstairs with the V. Okay. So that the problem that we propose to answer. And then there is this quantity m over q. That's the charge, mass to charge ratio. Okay, that's an important quantity that we can measure rather easily using a device called the mass spectrometer. Take a look here. Think about that. I'm gonna separate this equation here. Separate right like that. Right? So here you go. We have this quantity, the mass to charge ratio. Okay? We already know how to measure the velocity of the particle. Remember that's what we did last time using the velocity selector. Let's take a look. If you know, here you go, that's how we measure, not how to measure, we know how to calculate the velocity of the particle. If you you can adjust the electric field of a configuration, right, of a parallel plate, for instance. You do that just by applying the proper voltage in there. And then you adjust also the magnetic field in the region. If the magnetic field, if a particle has this velocity here in such a way that it is E divided by B, so you know what the velocity of the particle is just by using a velocity selector. So let's write that down here. We can find out V just by V of a charged particle. V of a charged particle just by using a velocity selector. Okay? The magnetic field. There are also some simple ways. We're not going to discuss that right now. To determine the magnetic field. But the ratio m divided by q is a little bit trickier. For this ratio, we to determine this ratio, we must use the velocity selector. Okay? Not the velocity selector. Not the velocity. Sorry. We have to use another device called the mass spectrometer. Okay? The mass spectrometer is a velocity selector combined with a uniform magnetic field. That's what it is. I'm going to show you how it looks like. What's that? Someone is flying low here. I have, some people make a living using this mass spectrometer. Okay, so let me show you how it, here you go. Remember that? That's the velocity selector, right? If the magnetic field and the electric field are just right, the net force applied to the particle is going to be zero. That's what you saw last time. This magnetic field here inside, I call the inside magnetic field. Magnetic field perpendicular to the electric field. Okay. Now, if you want, so just by getting the right magnetic field and the right electric field, we can find out the velocity, the speed of the particle. To find out the mass to charge ratio, we have to do something else. We have to use the velocity selector, and we have to put an outside magnetic field there. What you have here is just a slit to ensure that the particles that goes through this device is only the particles that has a velocity v. Okay? If the particle doesn't have this velocity v, they're going to deviate from the straight line path either to the left or to the right, and they are not going to be able to pass through this hole here. And then, now that we have a outside magnetic field, what's going to happen to this charged part? Don't forget the magnetic field is uniform. B out is different from B in, not necessarily the same. Okay, at this point here, what happens to the particle when it goes through the slit? V cross B is going to be, in this case, to the right, because we're talking about a positive particle. And you already know that this particle is going to describe a circular trajectory, a half circle trajectory. Okay. And it's going to strike the other side here of the plate. Okay. Now, this device, this plate that you see here, has some phosphorescent materials. Okay. Phosphorescent material that emits a greenish light. In general, it's green. The light is green. So if you're observing this device here and you see a green glow at this spot, you know that's because of this particle that's colliding against this this spot here, and you will be able to measure the radius, actually the diameter, right? The diameter of this circle. Divide by 2, you get the ratio, or the radius. Once you know the radius, you can find out what is the mass to charge ratio. Here you go. Right in here. Not this one. Right in here. Okay, here you go. This equation. You measure the radius with the mass spectrometer. You know the velocity because of the velocity selector, part of the mass spectrometer, and the magnetic field, you can adjust it to whatever value you want. So from this equation, you can find out what's going to be the mass to charge ratio. This is an important measurement because at the time that all this device was being developed, we didn't know what was the mass of the electron, we didn't know what was the charge of the electron, okay? By measuring R with a mass spectrometer, we can find the mass to charge ratio m divided by q, or here you go, it's going to be rb over v. So this type of measurement can be done with all sorts of particles. The first particle that we did that was with the electron. But we can do that with other particles as well. Remember, we are measuring, this device can allows you to measure only this ratio. It doesn't allow you to measure the m separately from the q, okay? That can be done, that has to be done in a different way. So next, go. Oh, and let's not forget, right? It is, okay, here is supposed to be the B out. Yeah, you gotta be very specific about that. Here you go. The magnetic field I'm talking about here is the external magnetic field. Whereas the velocity that we are talking about here is given by, this ratio, E divided by B. But the B is in the inner, okay? E divided by, here you go. Here you go. We can here write that. B in, B out times B in. Like that. That should be the, and let's see what I'm gonna do here. V, yeah, this is gonna be B out, B in, and that's gonna be the electric field. I don't need that. This one you can measure is the mass spectrometer. This one you control your own equipment. This one you can adjust with your own equipment. This one you can also adjust with your own equipment. Okay, so Okay, so here we go. We talked about the velocity selector, we talked about the mass spectrometer, and now we're going to talk about the cyclotron. Okay, there's another important instrument that we have out there. Let's take a look at the cyclotron. Well, we usually like to accelerate electric charges to very high speeds. Let me write that down here. Notes. So we talk about the following instruments. One, the velocity selector. Two, the mass spectrometer. We still have to talk about two more instruments. Two more instruments here. That's the cyclotron, and the Hall effect. Hall effect devices. We have Hall effect devices in our car, okay? Let's talk about the cyclotron first. You know, it's in today's world, we're required to accelerate electric charges to very high speeds, okay? And you know, for medical purposes, okay? One of them is for medical purposes. So how do you do that? How do you accelerate charges? That's the question you gotta pose to yourself, okay? You cannot accelerate a charge with a magnetic field alone because you cannot get the speed of a charge, you know, to increase the magnetic field alone, okay? You cannot, here you go, you're required to accelerate to a very high speed. You cannot increase the speed of an electric charge using the magnetic force alone. Why is that? Why is that? Because magnetic force does not do any work, right? The work done by the magnetic force is zero. So, one way to accelerate an electric charge is to apply an electric field. That you already know. Apply an electric field. So you go ahead, you build your parallel plate capacitor, apply a electric potential difference between those two plates. One plate is going to be positively charged, the other plate is going to be negatively charged. Put your charge within this field. The charge is going to start at rest, is going to accelerate between those two plates. Make sense? That's one way to accelerate the charge. If you want to accelerate this charge faster and faster, you have to either increase the field, okay, or keep the field constant and increase the distance between the plates. Make sense? Here you go. one way, right? One way to increase the speed of the particle is to increase the separation between the plates of the capacitor. Okay, let's go. No, we didn't do it. I'm gonna group it, and now I can increase. Here you go. The field remains the same if you have the strength of the field remains the same if you have the right potential difference, but this distance that the particle can accelerate is going to increase. Okay, here you go. Faster speeds. Here you go. Do you see what's happening here? Here you go. In order to accelerate a particle using the electric field, you have to make devices that are larger and larger. Faster charge with a larger device. Is a larger device. Okay, so that's one possibility. Okay. The other possibility, here you go, is to increase the electric field strength between those two plates. Two possible alternatives. Okay. And I'm going to illustrate here. Here you go. Stronger field, right? Larger density of field lines. Okay, so here you go. Faster charge, faster charge, faster charge with a stronger field, stronger E field. So two ways to increase the speed of a particle, either with a stronger field or with a larger separation of the plates of your capacitor. Okay, so let's write it down. Okay. So you cannot increase the speed of a charge, of an electric charge, using the magnetic force alone, because magnetic forces do not do any work. So one way to accelerate the electric charge is to apply an electric field. Okay. If you want to go faster and faster, you have two options. For the electric field. One, you either increase the strength of the field, or you increase the separation of the charged plates and keep the field constant. So that's two possible ways of increasing the speed of the particle. Okay, but either way, either solutions has some drawbacks. Either solutions have their own drawback. Okay? One, if you cannot keep on increasing the field indefinitely. You cannot keep on increasing the field indefinitely. Otherwise, you will run the risk of ionizing the medium between the plates. Okay? And what does it mean? Everybody has seen those electric discharges, right? Especially in a thunderstorm, right? So what those electric discharges is all about is ionized air between the clouds and the ground. Okay? When something like why does it happen? Because you have a very strong electric field between the clouds and the ground. When you have this electric discharge, what's going to happen to your parallel plate, you know? Your parallel plate capacitor. It's the ionized molecules here in between is going to uncharge your parallel plate. So that may not work for you. Okay? For this one here, right in here. What you see right in here is the air being polarized. The stronger the electric field, the molecules of the air becomes more and more polarized until you rip out the electrons from the molecules. That's when you ionized the material between those two plates. When something like that happens, the plates are going to become uncharged because the air becomes conductive, and any charge in the positive and negative plates here are going to conduct to the other plate, and you're going to lose the charge on the capacitor. Okay, so that's one drawback. The other drawback, for the other case, increasing the plate separation, you end up with a bulk device. Okay? So you have to look elsewhere, and that's what scientists have done. In order to prevent these drawbacks, scientists figured out a different way to accelerate charges without ionizing the medium or making the device too bulky. This is the cyclotron. They invented the cyclotron. What's the cyclotron? Cyclotron. Okay. The cyclotron combines the electric field to accelerate the charge, combines an electric field to accelerate the charge with a magnetic field to keep the device small. Let me show you how the cyclotron works. Okay? So here you go. Here is a drawing of the cyclotron. Right now, right in here. Okay, so it's a cylindrical device. Circular cross section. It has one D here on one side, another D, inverted D on the other side. And you have a gap between those two Ds. In this gap, there is an electric field. In order to have an electric field, you have to have positive charges distribution here and negative charges distribution here. So a charged particle that are placed here is going to accelerate from this point to this point. Everybody can see that, right? In addition to the electric field, they also create a magnetic field perpendicular to this plane. Okay? So in order to accelerate the particle, the electric field is going to do that for you. But then let's see what's the role of the magnetic field here. Here you go. Here this charge being accelerated, right? From one side of the gap to another. When it reaches the other side of the gap, what's going to happen? The particle is going to be subjected to a magnetic field only, a magnetic force only. And this particle is going to undertake a circular motion right in here. Can you picture that? So it's going to be accelerated from here to here. It's going to move with constant speed in this region of the magnetic field. And then when it reaches this point, what's going to happen? It's going to accelerate again. Okay? And not only is going to accelerate again, in order to accelerate again, you have to invert the electric field. There are devices that can do that for you. Flip the electric field back and forth. Okay? At this point here, the radius is going to be, smaller. Here you go. Let me see if I have, I have the radius. Let's see. Yeah, see the radius is slightly larger, right? Take a look. This radius of the radius of this pass with the radius of this pass, right? The radius of this pass is larger, right? The particle will undergo another circular motion at the spot, and it's going to accelerate again between the D's. That's how the cycle. Oh, don't forget to invert the electric field. The electric field must be inverted in synchrony with the position of the particle. Okay, so that's how the cyclotron works. So you can have several paths of this charge between those gaps that will make it accelerate faster and faster. You save on the space. You don't have to use very strong electric field that may ionize the medium that you have, okay? And your particle is going to be accelerated. That's the cyclotron. Here you go, the explanation. Okay, here you go. And those are all the equations. Velocity is equal to potential difference, Q over m, square root, right? And so on. Now, what's the period of one revolution? Let's take a look at the period of one revolution, okay? That's what we call the cyclotron, is related to the cyclotron frequency. It's going to be given by Vt equal to 2 pi r, okay? So here you go. It's a nice math that we can do. Cyclotron frequency. Okay, so here you go. Okay, cyclotron frequency, slash period. Let's calculate the period first. The period is going to be V times T. Okay, times 2 pi r. Period for a full revolution. Okay. But we calculate the r before, right? Let's take a look what the r is. We calculate the r right in here. We go. Right in here. and we can plug this r in the above equation. Okay, here we go. R. And look what a nice thing that happens here. So yeah, plug this r right in there. It is the v of the velocity of the particle that's changing every time it goes through the gap, right? But the period doesn't depend on the velocity. Do you see that according to this equation? So it doesn't matter how fast the particle is being accelerated. The period of revolution of your charged particle doesn't depend on the speed of the charge. Depends only the mass to charge ratio and the magnetic field. Okay? And now, knowing that, we can build up devices that that can synchronize the position of the particle in terms of this frequency, in terms of this period. Okay? So here you go. All you have to do is, since the particle is moving half of a circle, we can keep on flipping the electric field at every period divided by 2. Okay? Don't forget the frequency, cyclotron frequency is the inverse of that. Okay. QB over 2 pi m. Let's see. QB over 2 pi m. That's the cyclotron frequency. Let's see if we have something else. It's time for our break, right? Yeah, let's take attendance first. We go. Go out, delete. Yeah. Excel. Here you go. That's what I want. Today is the 19th. Okay, Maria Acevedo not here, right? Toby is here? No. Harun? There. Musa? There. Genesis? There. Jennifer? No, Jennifer. False. Robert False here? Here. Pedro Flores? Here. Lawrence Flores? No? Oh, just walk out? Okay. Okay, Alexander Garcia? Sung? There. Brian Inez? Athena? No. Dylan Martinez? I'm gonna pause the recording here. Okay, so we are back here recording. So let's finish the cyclotron, right? So every time that the particle passes through this gap between the D's, it's gonna increase the speed. Every time that it increases the speed, it's going to increase its radius of curvature. Okay, increase the speed here, increase the radius. The largest possible radius that the particle will be able to travel is going to be the radius of the cyclotron. Okay? And and then you can find out what's going to be also the maximum speed of this particle as well, just by given by the radius. So let's take a look at the equation here for the radius that we saw before. Here you go. That's the radius here of curvature. So when the particle has a radius of curvature equal to the radius of the cyclotron r, the speed is going to be given by this equation here, okay? So what will be the maximum speed of the charged particle in the cyclotron? Okay, in the cyclotron, here you go. The maximum speed will be given by the radius of the cyclotron. When lowercase r, right? When lowercase r is equal, when lowercase, heck. When lowercase r is equal to big R, the radius of the cyclotron r. Okay, when lowercase r is equal to r, the particle will have the following speed. Here you go. Lowercase r equal to big R. And then we go ahead and invert this equation, QBR, QBR. Okay, M divided by M. Okay, that's gonna be my speed. Remember I told you about the mass to charge ratio? You know, it's showing up almost all the time, right? It's gonna be the maximum velocity of the particle in a cyclotron. Oh, maximum velocity of the particle in a cyclotron. Qm over Br. The stronger the the stronger the magnetic field, the faster the particle can travel. Of course, the larger the radius of the cyclotron, the faster the particle is going to travel as well. Okay? So the stronger the magnetic field means the stronger the magnetic force. So that's our conclusion for this cyclotron. Those are very simple math. You know, those are, you know, advanced devices that have a rather simple mathematical explanation. And what else we gotta do? So velocity selector, we did the velocity selector, we did the mass spectrometer, and we did the cyclotron. Now we are going to talk about the Hall effect device. There are Hall effect devices out there. You use one on in your car. Okay, so let's see how it works. It's a very interesting, you know, device. Let's see if I have it, the drawings. Let's see. Okay, right in here. That's the one. So we start with a plate, like this one. Okay, and then we pass an electric current through this plate. It's not a wire, it's an actual plate, okay? It's an actual plate. And then what do we do? Here you go, the electric charge, the electron, is actually traveling in the direction opposite to the current, right? What else do? We apply a magnetic field perpendicular to this plate. And something interesting happens when you have a current passing through this plate. Something interesting happens. Okay, we're going to have a magnetic force pulling the particle downwards. V cross B is upwards, but because it's a negative charge, the electron is going to pull downward, going to be pulled downwards. Okay, here you go. And then you're going to have lots of electrons being populated there at the bottom. Let me, we're gonna have lots of electrons being populated out at the bottom. Okay, here you go. More and more electrons. Let me just illustrate the electron for now. Here you go. Not only you have electrons, but you know, if you are having electrons being pulled downwards, it means that you are losing electrons here at the top. Okay? So by the same token that you're going to end up having electrons going to the bottom, you must also have additional positive charges building up at the top. Not because the charges, the positive charges are migrating upwards. No, 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 no. That's because the negative charges are migrating downwards. Remember, positive charges are two protons. You know, the protons are positive charges and they are too heavy to move in an electric circuit. So it's only the electrons that are moving the electric circuit. So what we have here, we have an excess of positive charges because the negative charges have migrated from the top to the bottom. What you see right in here is the Hall effect. Just by applying a current to this plate right in here and a magnetic field, you create a separation of charges that create a difference in potential. And this difference of potential can be measured with a multimeter, okay? So once we have this disposition of charges, what you're going to create? You're going to create an electric field. Can you picture that? If from, if you have a magnetic force pulling those charges downwards, as more and more charges build up on the top and bottom, you're going to create an electric field. This electric field is approximately uniform. It's approximately uniform. And then what's going to happen? You're going to have also, not only going to have a magnetic force, you're going to end up having an electric force as well. Initially, this electric force is going to be less than the magnetic force because you do not have enough charge distribution at the top and bottom. But eventually, you're going to have so many charges at the top and the bottom, so many charge distribution at the top and the bottom, that the electric and magnetic field are going to cancel out. And no charges are going to be deflected from their path anymore. That's what we call a steady state condition, a steady state, the system reaches a steady state condition. Okay? And like I said, because you have this difference of electric charge, there will be an electric potential difference as well. Let's see here. Yeah, here you go. You go ahead, and this is a type of phenomenon that can be measured with your multimeter. Negative, and we even have a very nice video here that I want to show you about the Hall effect, how something like that happens in real life. Negative, negative, okay? So current passing through this plate. This plate has a certain thickness T, and with D, you can measure this electric potential difference. So how do we do that in real life? Now there is a video out there on YouTube that uses a gold leaf and copper plate. Okay, that's a copper plate, and here's a golden leaf, and you can look there. I'll try to show that to you there upstairs. Okay, and what else you have to do? You can do here. See, yeah, that's what you have. Let me make some derivations here for you. So that's the whole idea about the Hall effect. There are devices that use this phenomenon of the Hall effect out there. Okay, let's see, going for 28. We have one more thing to do. Let me see what that is. Magnetic force in a current as well. Okay, and what about the Hall effect? Hall effect must be way down here. Yeah, here you go. Here's the Hall effect. Okay, so this steady state condition is achieved whenever the electric force is equal to the magnetic force. Okay, QE is equal to QVB, and we have an equation similar to what you saw before for the velocity selector. When the velocity of the charge is this one here, and the electric and magnetic field obeys this relation, then you have a steady state condition. Okay, so here's another equation. The electric field is uniform. Okay, it's roughly uniform. It's a very, very good approximate for what happens in this device. So because the electric field is uniform, there is a very simple relation between the electric field and the electric potential. Electric potential is E times D, just like you saw in that first experiment of ours. And the electric field can be rewritten as V of the Hall potential, right? Divided by D. And here is going to be the velocity of your charges. Okay. With this experiment, one of the things that you can do is this experiment, okay, is to find out, let's see here what's going on, is to find out what's the concentration of charges that, or what's the number of charges that you have in a given metal, those charges that are free to move and you are used for the current itself. Okay. Okay, so what time is that? 6:45. Let's see how we are doing here in this. Yeah, we still have more to go. Let's meet again on Thursday. Okay, we finished this chapter 29. We could not finish today. And then there is a little bit more to talk about. Okay, so here you go. What we have discussed. Hall effect, devices. Okay. Then next time we're going to talk about magnetic force in a current. Okay. And there are different current configurations that you have to know. You go. See, you have a loop of current. This when it's subject to a magnetic field is going to experience a force, and before I'm gonna cover that. Here you go, magnetic force in this other current configuration, and all comes from the magnetic force law. It's not that difficult to understand. Okay, and then when you do that, we can move on to chapter 30. So I'll see you upstairs. Okay, magnetic field.